Introduction to composite functions. What's a composite function? First, I want to go over what a function is. On the left here, I've got f of x equals x squared minus 1, a basic parabolic function here. I put in -3 for x. -3 squared is 9 minus 1. I get a resulting 8, as you can see here. I put in -2 for x. -2 squared is 4. 4 minus 1 is 3. And I've graphed this right here. On the right, I have a function, just a series of lines put together. -4, -1 is right here, from this right here. -2 and -1 is right here. -1 and 0 is right here, crossing the x-axis. And these are both functions. They're connected, and we're going to learn more about what a function is as we go on through these slides. Now, when we look at a function versus a non-function, you see this little series of ovals right here on the left. A function will have an input, which is the purple right here, and 1 goes to P, 2 goes to Q, and 3 goes to Q. Now notice that I got both 2 and 3 going to Q, but that's okay. I only have one exported line coming from each input. This is the input, the purple right here. This is the output, this green right here. And I can only have one exported line coming from each individual input. That makes it a function. On the right here, it's a non-function. I have 1, 2, 3 input on the left and P, Q, R on the right. And what makes it a non-function is this number 2 right here. It is going to P and Q. I can only have one exported input going to an output, and I have 2 here. I don't know which decision is going to go. If I pick 2, does it go to P or does it go to Q? And that makes it a non-function. The vertical line test is graphically the simplest way to determine if it is a function. If I have a vertical line on this first equation right here, this is basically a linear equation, and the vertical line test, my dotted line right here, can only cross at one point instantaneously. It only crosses at one point right here. It only crosses at one point as it moves from left to right here on this upside down parabola. These are functions because that vertical line only crosses our equation at one point anywhere. Now, a non-function right here is looking at this oval right here in the first one. The vertical line test, it crosses both here as well as here. And if I have the vertical line moving left to right anywhere, I'm going to have that same issue. I got this sideways parabola, which is basically x equals y squared. And it's crossing here, that vertical line, as well as here. So this is not a function. Equations, yes, but neither one of these, this oval nor this sideways parabola, are functions because the vertical line test says they cross at more than one point. We can also do a table test. The table test is basically looking at a table, an input and output table, to determine if it is a function. On the left here, this is f of x equals x squared. So basically, you're looking at our first slide here. -3 goes to 9, -2 goes to 4, -1 goes to 1, 0 goes to 0, 1 goes to 1, 2 goes to 4, 3 goes to 9. Notice each input, which is the x here, only has one output answer. Same thing right here. 1 goes to 2, 2 goes to 4, 3 goes to 5. And really, there's only one unique number across both of these here. We don't see the same number twice. Now, Yes, negative 3 goes to 9 here, and 3 goes to 9 here. But the negative 3 only has one line going output. Say there's a 3 going output. 2, I have a 4 here, and a 4 here. But I've only got negative 2 going to 4, and I got 2 going to 4 here. Each individual line, our input, has only one line going out. Same with these. I got 13 going to 12, and 15 going to 12. And that's allowable. I only got one line from each input going outward. But if I look at this equations on the right here, x squared plus y squared, and by the way, that is the equation of a circle. If I look at this, and you can think about a circle, we're going to have more than one place where it crosses that vertical line. Guess when I put in 2, I get 0. When I get negative 2, I also get a 0. When I get 0 here, and it goes to 2, and 0 goes negative 2. So I don't know where 0 goes to. Should it go to 2 or negative 2? This is all right. But this right here is not. Nor is this one. Negative 1 goes to 1.732, or negative 1 goes to negative 1.732. 1 goes to 1.732, and 1 goes to negative 1.72. Each of these inputs, that 1 is going to multiple outputs. I don't know which one it is. Does 1 go to 1.732 or negative 1.732? Same as negative 1. Does negative 1 go to 1.732 or does negative 1 go to negative 1.732? 0. Does 0 go to 2 or negative 2? And same thing with here. I got a 1 that goes to 2 and a 1 that goes to 4. Which one should I go? Well, and then I go this way as well. And I got 9 that goes to 9 and a 9 that goes to 12. Which one do I go with? Well, I don't know. That's what makes it a non-function. Now, what's a composite function? We've already determined what a function is, but what is a composite function? A composite function is also known as a nested function. It's a function within a function here. Let's go back to our previous two functions here. This first one, f of x is x squared minus 1, a parabola. And this is a simple line function right here for the second function. Now, when we look at a composite function, and we're going to call this one, if you notice here, this one is f of x. This one is g of x. And if I look at a composite function, as I said, it's also known as a nested function because it's nested within there. This f of g of 2. What this says here is first the nested function, the one that's inside, is the g function, this one right here. And we got to see what g at 2 is. G at 2. Well, here is my g right here, this entire graph right here. And g when x equals 2, here is 2 right here, x equals 2. The g of x equals 1 right there. So g, see if I write this out properly here, at 2 equals 1. Now that 1 is going to be what I put in to the outer function, f of x, right here. And wherever I see the x, I replace that with 1. So if f of x equals x squared minus 1, I would put in 1 squared, because I'm replacing the x with that answer from the nested function, minus 1. And then 1 minus 1 would equal 0. Trying to put an equal sign here. And we can look at the graph here. I'm sorry, I'm having problems making a 0 here. Not very good to manage there. There's a 0. So, but we can look at manually 2, when I put in g of x at 2, g for 2, I get 1. And when I go to 1 here, here's my 1, my y, or my f of x, which is my y, is 0. So I just produced graphically as well as algebraically. And that's what I did here. You could see g of 2 equals the 1 right here. And when I put in, again, when I put in x for 2, I get 1. That 1 goes right here. That replaces the x. So it would be, instead of x squared, it's 1 squared. And 1 squared is 1 minus 1 equals 0. And like I said, you can do this algebraically, you can do it graphically. Again, when I put in 1, here's my new outer function. I get my x is 1, and my f of x, which is my y, my resulting, is 0. So, composite functions are usually seen as equations. And as I said before, it's a nested function with one equation nested inside the other. I've got two equations here. G of x equals negative 20 minus 3x. And h of x equals 1/2 to the x. And then we want to find g of h of negative 2. H is the inside function, the nested function. And we got to find h at negative 2. Well, my equation is 1/2 to the x right here. And my x I'm looking for is negative 2, as we found here a moment ago. 1/2 to the negative 2. And when I have a negative exponent, that makes it reciprocal. So that would be 1/2 squared is 1/4. But the reciprocal, but so a negative 2. So that makes it actually 4. 1/2 to the negative 2 is actually 4. Because it's 4 flipped, 1/4 flipped. So my inner function, h at negative 2, equals 4, as I found here. I'll put that 4 in for the new x into the outer function out here. Put in 4 for x. So that is negative 20 minus 3, and that was x3, negative minus 3x, which is now it's 3 to negative 4, minus 20, and negative 3 times 4 is negative 12, becomes minus 32. So g of h at negative 2 is minus 32. Here's another one. Composite functions are usually seen with equations. And again, we're doing the nested component. And I'm looking for a f of h of 12, which means the nested function is the h of t right here. And wherever I see a t, I'm going to put in 12. So my first equation, my nested function, is 24 over t. T is 12. And when I put in 24 over 12, that's 2. That 2 is now going to be the x, or the t in this case, in the outer function, which is t squared minus 10t. So every time I see a t, I replace it with a 2. T squared minus 10t, where t equals 2, which was our result in our nested function. T squared, I see a t, 2 goes in there, 2 squared, which equals 4, minus 10 times t, or 10 times 2. So it's 4, 2 squared is 4, negative 10 times 2 is minus 20, 4 minus 20 is 16. So my resulting composite function is f of h of 12 equals negative 16. Here is a rational function right here. F of t equals t over t minus 8. And then h of t is negative 2t. And I see f of h at negative 5, the nested function being the h function. and I'm putting -5. So -2t is the nested function. Where I see the t, I replace it with -5. -2 times -5 is +10. That 10 is put in the outer function right here. So wherever I see a t in the outer function, the f of t, t over t minus 8, I'll replace t with 10. So it's 10 over 10 minus 8, t minus 8, which is 10 over 2, which is 5. So with the nested function f of h at -5, the result is 5. Now, where do we use composite functions in the real world? If you think about this, they're more commonly used than you would think. I remember in 1989, the Exxon Valdez, which was an oil supertanker, ran into a coral reef in Alaska and spilled millions of tons of oil. Actually, I should say barrels. They call it by barrels. But if you think about this, oil floats. So it's how much oil gets on the surface, which is going to affect all the sea life, birds, animals that need to get through the oil to breathe, the oxygen, and stuff that lives on the surface. There are two components going on. The first component being how much oil is coming out, being spilled out where the coral ran into it, and secondly, that surface area. So we can actually figure out, it's a composite function here, the oil spread slick. How quickly is it spreading? If I know it's coming out a unique rate, the rate of the oil growth is spreading at a rate of 10 feet per minute. And it spreads in a circle. If you put oil in water, basically it's spreading out because it floats. Now, the area of a circle is defined as pi r squared. Now, if it's going at 10 feet per minute, that's coming out. How big would it be in 100 minutes? Well, my one equation is how much is spreading against the area of the circle. And my other equation is it's going 10 feet per minute. We'll call it t as time. So if we know it's for 100 minutes, that would be 10 times 100 or 1,000 feet coming out. And what's the area of 1,000 feet? Well, that would be pi r squared. It would be pi times 100 squared. Or I should say, pi times 100 squared, which is 10,000. And we'll say pi is 3.14 roughly times 10,000. In 100 minutes, it's going to cover 31,400 square feet. And from there, we can determine what kind of bio life is going to be affected. We determine, you see, seabird mortality is one of the things they looked at here. And you see, it's a direct growth. It's a linear equation. Another example was hazardous wastes. Back from 1850 up to 1940, there was, up in New York, in Love Canal, they had 55-gallon drums full of highly dangerous chemical called benzene. It's one of the most corrosive chemicals there is, also one of the most carcinogenic. Now, the benzene is acidic and will slowly break through the oil drum. Now, they buried this back, like I said, the 1850s up to 1940s, and there was no EPA back then. In fact, the EPA was created because of this issue. What happened was, the 55-gallon drum has a thickness of 0.92 millimeters, which is a millimeter, by the way, is 1,000 microns. So it's 920 microns thick, a 55-gallon oil drum. The benzene will corrode the oil drum, which is made of steel, at 20 microns per year. Well, you can also figure out it's going to, how many years will it take eventually corrode through if it's eating at 20 microns per year, and the steel oil drum is 920 microns thick. That's pretty easy to figure out. But the real function that we're looking at here is the rate of leukemia, because benzene is highly notorious for causing leukemia among children. So it could corrode through 75 years. We want to know how bad the leukemia rates will be based on the corrosion of the oil drums. So when we look at this, we got composite function, the CFT equals 20T, how long to corrode, and then the rate of leukemia right here. And they figured out here 154,523 deaths of benzene, primarily through various cancers, including leukemia, after 75 years of burial. Love Canal was done by was actually built as a subdivision in the 70s. It was bought by the school board in Upper Niagara County in New York. They never could develop a school there, so they resold it, and there was no real information about all these oil drums with with benzene buried in it. And Hooker Chemical Company sold it to the school district, and the school district never developed it, so it was built into, it was resold to some real estate, and they built homes on it. And unfortunately, these homes were built right over where these oil drums were. And Niagara Falls School District just sold it for $1. What's interesting is they inserted a disclaimer denying any liability for any waste or problems with the soil. Hooker Chemical told the school not to disturb the site because of the toxic waste. And when they had so many cancer rates among people at such a high rate, which I'll show you in a minute here, they had abandoned it. It's still abandoned to this day. So this is 44 years later, and they had to basically have to dig up and burn the soil. And it created the first Superfund site for clearing up waste. And the problem is, it's costing even more to go through cleaning up than it would have been. Here are some graphs of the actual problems that this benzene leakage caused. As you can see here on the left, this is preterm births. This is actually right here in the Love Canal area, number of preterm births. This is preterm births in the rest of the Niagara County. And this is upper New York. So you can see there was a significant cause of preterm births where Love Canal was. Same thing with birth defects in Love Canal, especially among boys, compared to the rest of Niagara County, where Love Canal sat, the county was in, and the rest of upstate New York. So definitely a lot of issues going on. And in fact, when you look at a lot of the cancer rates, they are much higher, the blue being the Love Canal, and then the orange being the rest of upstate New York. You saw higher areas in lung and other respiratory, slightly higher in stomach, and then you can see where cervix, uterus, ovary, prostate, bladder, and other genital urinary organs had higher rates there as well. So definitely there was a problem here. And that was really the issue with the benzene. When they dug up the Love Canal area, this is all the oil drums they found. There were just literally thousands of them, a lot of them corroded through.